When the facts change, I change my mind. What do you do, sir? Well, this is a famous quote, not by me, but by John Maynard Keynes, one of the leading economists of the 20th century. So in this section, we're going to consider something called Bayesian updating. And this is really at the heart of what we are all doing throughout our lives. We may not realize it, but we are updating our beliefs in light of new information. Now, of course, we're going to look at things from sort of a pure statistical perspective, perhaps, but nonetheless, we always learn from our mistakes, hopefully. And we hopefully make better decisions as we go through our lives, as we learn more about the ways of the world. So, let's consider a very simple example to begin with. I return to the rolling of a fair die. So remember, the sample space has 6 equally likely outcomes, those scores 1, 2, 3, 4, 5, and 6. We derived its probability distribution previously, and let's suppose an event of interest is rolling a 6. Suppose we win a prize if that particular outcome occurs. So immediately, from that probability distribution, we can identify that the probability of the event A, where here we're going to define A as rolling a 6, that probability of A is simply 1 over 6. Now that hopefully is fairly straightforward from the work we've covered previously. But let's suppose I give you a little bit of information. Suppose I told you that when I rolled this die in secret, so you didn't see what happened, suppose I told you that an even score occurred. So armed with that information, are you able to update your beliefs, i.e. what is the revised or updated probability that a 6 occurs? Well, let's break it down and think about it in terms of sample spaces. So to begin with, before I gave you this extra piece of information, you knew that there were 6 equally likely scores for this die. And you came up with that 1 over 6 probability of rolling a 6. Now let's imagine you are now told, indeed, that an even score has occurred. This allows you to revise or update what the sample space could be. Because if I tell you that an even score occurred, we can eliminate the possibility that the score was a 1, a 3, or a 5. The 3 odd possible scores, which means whatever the outcome was must have been either a 2, a 4, or a 6. So there is still uncertainty. We don't know for sure which outcome has occurred, but we have been able to eliminate 3 of those possibilities, namely 1, 3, and 5. Well, given those 6 original outcomes were equally likely, if we've now reduced this to just 3 possible outcomes, 2, 4, and 6, they themselves are still also equally likely. But now we only have 3 rather than 6 equally likely outcomes. So continuing with our classical probability theme, i.e. consider the size of your sample space and then simply count how many of those elementary outcomes agree with your event of interest. Well, given 6 represents just one of the 3 possible outcomes in this instance, then the revised or updated or conditional probability of obtaining a 6, given that an even score has occurred, would now be 1 over 3. So here we see our first sort of real example of Bayesian updating. Namely, we have an initial belief, we receive some new information, and we revise our beliefs, in this case in a probabilistic sense, in light of this new information. So now I'd like to introduce the notation to represent a conditional probability. So in the unconditional setting, we had the probability of A equal to 1 over 6. Now I'd like to introduce the conditioning, this receipt of new information. So if we let B denote the event that we get an even score, then we can write the probability of A given B. So this sort of vertical line, this bar, represents a conditioning situation. So now the conditional probability of A given B we've derived to be 1 over 3, a third. So in this instance, the revision to the probability of A has been upwards, because knowing that an even score has occurred means it's more likely that we got a 6 than if we didn't know that information. But don't think necessarily that revisions to probabilities will always be to increase them. Of course, they could go in the opposite direction. Suppose I told you instead of an even score that an odd score had come up. Now, in fact, here, the fact that we get an odd score we can think of as the complement to event B, if you like, the opposite to B occurring. because every score must either be an odd score or an even score. So if it's not even, of course by default it must be odd. But if you knew an odd score had occurred, that must mean that it was either a 1, a 3 or a 5, and hence there is no chance that you could have rolled a 6 in this instance. So armed with this complementary event, if we wrote now the probability of A given the complement of B, then of course this probability is now revised down to 0 because it's an impossible event. If it's an odd score, there is no way that you rolled a 6. So this idea of Bayesian updating is to collect new information, hopefully relevant and useful information about the world, and then update our beliefs accordingly. So perhaps we should round off with a revisit of our now famous Monty Hall problem, because I gave this to you as your sort of first example of decision making under uncertainty. Well, this at its heart is involving Bayesian updating. Now, in the accompanying resources you'll find online, I'll explain the theory in a little more detail. But at the big picture level, let's just consider these revised probabilities. So remember those 3 original doors, A, B and C, to which you assigned prior probabilities of a third to the sports car being behind each of those 3 doors. So those are what we call the prior probabilities, the initial state of the world. You then chose, in our iteration of the game, door A, and I opened door B. So my action of opening door B gave you some new information. You learnt something which you did not know previously. So armed with this new information, and of course here useful information, we are now in a position to revise and update these probabilities that the sports car is behind either door A, B or C. Immediately, I think we can assess that the probability it's behind door B, once a goat, say, has been revealed, of course, it must be a revision of a third down to 0, because it is impossible, given you observe the goat behind door B, that a sports car lies behind it. We also said the initial choice of door A remained closed because those were the rules of the game. I said I would not open whichever door that you chose. So if you chose door A, I was prevented from opening it. So there was no new information about door A. It stayed closed because you chose it, and hence that precluded me from being able to open it. So if there's no new information, then of course the probability associated with that particular outcome cannot change, and so it remains as a third. So the unopened door C, there was some information revealed to you there. Now, of course, many people don't see this new information attached to door C because they don't see any physical change to door C. It was originally closed and remained closed, unlike door B, which you actually saw it physically being opened, and it was revealed what was behind it. But as we said, there were 2 possible explanations for why I opened door B in the first place. If the sports car did lie behind door C, there's no way I'm going to reveal that to you, and hence with probability 1, with certainty, I would have to open door B. So that is one possible explanation. Of course, the other possible explanation is that the sports car was behind door A all along, and hence we have 2 goats, one behind door B and one behind door C, and hence I would be indifferent as to which door I subsequently opened, and I'd sort of randomise between those 2 doors. Effectively toss a fair coin, let's say it's heads, 50% chance of that, I would open door B, and if it was tails, 50% chance of that outcome, I would open door C. So that action of door B being opened meant new information was provided to you, and it would allow you to update your beliefs probabilistically here in the Bayesian setting. So in the accompanying online material, I give explicit details about how these probability calculations are derived. But to begin with, at the big picture level, just appreciate that in life, as we learn new things and receive new information, that the rational thing to do is to take that on board and revise our beliefs about the world accordingly. Perhaps just conclude with maybe another example. When you're deciding what to wear on a given day, no doubt you perhaps listen to the weather forecast. And the weather forecaster cannot know for sure whether it's going to be raining or sunny tomorrow. So there's some uncertainty in their decision making, some uncertainty in the forecast they provide. Of course, though, if you have a weather forecaster who has a good reputation, they won't predict the weather correctly every single time. No one is perfect. There's no certainties in life, as we said, just those deaths and taxes, of course. But there's no certainty in weather forecasting. But if the weather forecaster gets it right far more often than he or she gets it wrong, then you tend to trust the forecast they give you. So, before you listen to the forecast, the weather forecast, you may have some initial thinking about what you're going to wear or what activity you may do tomorrow. And then you listen to the weather forecast, and if that is giving you some new information, perhaps you listen to the forecast, let's say, of a lot of rain tomorrow, and perhaps you weren't anticipating that, and hence you would take on board this new information, albeit imperfect information. It's not a perfect forecast necessarily, but then you may take that on board and adjust your behavior accordingly. So if you were deciding, let's say, to go to the park, thinking it was going to be a nice day tomorrow, but then you tune in to the weather forecaster who predicts torrential rain, then no doubt you'll sort of update your beliefs accordingly and revise your behavior. So we'll say a bit more later on in the course about this receipt of new information. There are many applications of this we can provide. We will see an interesting one with regards to share prices and how they would react to new information being received by the market. So conditional probabilities introduced here, a major topic, but it's great, I think, for you to start to appreciate how we can change and revise these probabilities as we learn new information about the world around us.